Merkle trees. What are they and how do we use them? A binary tree is a tree structure of data where each node has two children. A complete binary tree is a binary tree that has all of its members filled. A Merkle tree is a complete binary tree where each node is the hash of its left and right children. Here I've got some code courtesy of Alejandro Mira, and this prints out a ASCII representation of a Merkle tree. Now the root, as per the definition, is derived from hashing all of the left and right children. So starting from the base layer, hash those two to get this hash those two to get that hash, and then so forth with all of the leaves. And then once you've got the next layer, you continue the process. So hash the left child with the right child until you've done all of them. And then eventually you're down to the root. The depth of the tree is the number of layers, and that number can be derived from the number of leaves. The log 2 of 16 will give you 4. To create a Merkle tree, you will also need to pad out the data, as it needs to be a complete binary tree. So here I've got 9 leaves. Those 9 leaves need to get padded out, and it's padded out just by repeating the last element. If I happen to have an even number, then the padding out happens at the next layer, which is equivalent to copying the pairs of leaves. Obviously in your code you're not going to have a structure like this. So I have a class here for a node, but that's merely to facilitate the visual representation of it. You're going to want to array, so from left to right, bottom to top. So all of the elements of the first layer, then all of the elements of the second layer, then the third layer, and finally the last layer. Now we come to the crux of why a Merkle tree has use. So in order to prove that we have a hash that is part of a set of data, we can use a Merkle tree. And the benefit of a Merkle tree is that to prove that we have a hash, for example this hash here, we only need 1, 2, 3, 4 other hashes to calculate the root and thereby prove whether or not we have that hash. So for example, to prove that the hash 5c, which is at index 3, exists in this Merkle tree, we need the hash at index 2, 16, 25 and 29. Would be to hash your leaf with the hash at index 2, the next hash at index 16 with that obtained hash, then you would hash the obtained hash with the index at 25, then you would hash the obtained hash with the index at 29. You will need to always hash in the same order, so from left to right, so the left child is always concatenated with the right child and then hashed together. So the order is important, and you can work out the order by dividing the index by 2, as each layer is being reduced by a factor of 2. So your index will be reduced by a factor of 2 as well. So if your index here is 3, your index here will be 3 divided by 2, rounded down, and then again the index 1 divided by 2, rounded down, and then again. So the reason why an index Merkle tree is useful is because you can efficiently prove whether or not a hash is part of a collection of hashes. So if you were to roll up a bunch of transactions simply by getting a number of hashes equal to the depth of the Merkle tree, you can prove whether or not your particular transaction is within that rolled up group of transactions.